Hey guys, how are you doing? Today's class lesson is going to be focused on energy and the forms and changes of energy. Our Georgia Standards for this particular section of our unit focuses on being familiar with the forms and transformations of energy, such as the law of conservation of energy, relationship between potential and kinetic energy, and also being able to compare and contrast the different forms of energy and their characteristics. So make sure you have your Cornell notes ready to take. Make sure you write down any questions you may have. Take good detailed notes and summarize that lesson. Make sure you have your TUSC number also, okay? Let's begin. So let's talk about energy. Energy is the ability to do work, and I don't mean having a job, but work is just transfer of energy. And energy and work are always expressed in the units of measurements called joules. In the illustration, you can see the tennis player does work. She's using a racket, and she's transferring the energy that she has to the racket, and with that energy, the racket can do work on the ball, like hitting it. And the law of conservation of energy basically says that energy can be neither created nor destroyed by any ordinary means. So it only transforms from one form to another, or it can be converted from one form to another. As we go on this lesson, you'll find that energy can be transformed multiple times, not just two. So if it appears that energy is disappearing, it really isn't. They're just finding new ways that energy is being transformed. So basically all the forms of energy can be placed into two main categories. We have potential energy, which is stored energy that can be put into future use. And we also have kinetic energy, which is the energy of motion. So something can start out stored or potential, but once you make it change, or it changes from one thing to another, it has kinetic energy, and it also can return back to potential energy. As you can see in the examples below, on the left hand side, the bow and the string all have energy that is stored because the archer is pulling it back, so he has energy stored in there. But once he lets go, that potential energy is doing work. Therefore, the arrow moves, you have kinetic energy. And same with the picture on the right with the hammer. The person is pounding the nail into the wood. The hammer has kinetic energy because it is moving, it's doing work, and it's driving the nail into the wood. So there are two main forms of energy, and they can fall into either kinetic or potential. So as we go through, you'll learn that certain types or forms of energy can either be kinetic or potential. Let's talk about the first, mechanical energy. Mechanical energy is the total energy of motion and the position of an object. So basically, mechanical energy is potential plus kinetic energy. Now, to calculate kinetic energy, you need to know the mass, the velocity. So you take the mass and you multiply it times the velocity square, which is velocity is the speed of an object, and that's how you calculate the kinetic energy that an object has. Now, do you think mass or velocity have a greater effect on the kinetic energy? Well, if you said velocity, you're absolutely right. If you look at the formula, velocity is squared. So anytime you square an object, you're actually increasing it 4 times. So the object has more impact on kinetic energy if its velocity is greater than the mass. So basically, the more mass or high velocity, the more kinetic energy. The more mass and higher up above the ground it is, its resting position, the more potential energy. Potential energy is also calculated by multiplying the mass times the gravity times the height. So you take the mass of the object, how high up it is, and the acceleration due to gravity, which on planet Earth, the acceleration is always going to be 9.8 meters per second squared if you want to be a precise person who wants to calculate it accurately. But you can also round it to 10 meters per second squared if you don't want to be as precise. When you calculate the potential energy, again, it's always expressed in joules. Let's look at this illustration. Here you have a basketball. The basketball is being thrown into the air. Once it reaches its height, before it starts to go down, it has reached its maximum potential energy. So the higher up the ball is, the more potential energy it has, and once it starts moving, it reaches maximum kinetic energy. So the ball slows up as it goes up, and then it speeds up as it comes back down. Potential energy that is depending on the height is called gravitational potential energy. That is calculated by taking the weight times the height. As you can see in the illustration on the right, we have the Horseshoe Falls, which is located in Niagara Falls. So a suspension bridge or even a fallen snowflake all have gravitational potential energy. Take into consideration this illustration. Here you have a diver. If the diver is on a 3-meter high diving board, you have 3 times the gravitational potential energy than one diver who may be at the 1-meter diving board. So if you want to have greater potential energy to have that greater effect on your jumps or your flips, you want to be on a higher diving board. So you've heard that saying, the bigger they are, the harder they fall. I think there was a movie about that. But anyway, it is true. Objects with more mass have greater gravitational potential energy. Again, that formula, weight times height. Let's see if you can put your skills to work. Use a diagram to answer the question below. Each ball has the same mass. Which ball has the greatest potential energy? Take into consideration what we just discussed about the formula. I'll give you about 10 seconds to think about that. I think I gave you more than 10 seconds. Alright, so if you said ball D, you are correct. Ball D has the greatest potential energy, and that's because it's much higher up than the other balls. So basically what we're trying to say is, since the gravitational potential energy of an object is directly proportional to its height above the zero position being the bottom ground or the floor, then the height is doubled, so you double the gravitational potential energy. If you triple the height, you have triple the gravitational potential energy. Our next form of energy is thermal energy. Thermal energy is the energy of moving molecules. All matter is made up of molecules and has thermal energy. Doesn't matter how fast or how slow it's moving, it still has thermal energy. If you take a look at the diagram at the top right, you could see hot or molecules that are moving very rapidly, like in gas, they have more kinetic energy than colder objects, which the molecules are still moving, but they're pretty much in the same spot. They're just kind of vibrating next to each other. So it doesn't have as much kinetic energy. A good example of that is water. Now, on the left-hand side, you have an ice cube. It's made of molecules, but those molecules are pretty much in the same position, locked tight, but they vibrate, so not as much kinetic energy. When they start moving a little bit more fluidly, as if a lake, then the kinetic energy has increased, but not as much as our far right picture, which is particles of water in steam. They move a lot more rapidly, so they have a lot more energy than a liquid or a solid. Electrical. Electrical energy is the energy of moving electrons. Now there are 2 main types we'll talk about, static and current. Static electricity is your everyday lightning bolt, which, did you know that Florida is the #1 lightning capital of the world? Anyway, current electricity is pretty much what you see in your home or in your car, where you have to have series of parallel circuits. So those are all moving electrons, still energy. Sound, one of my favorite forms of energy because I love music. Sound energy moves through vibration of matter. It travels in different types of waves, but this particular type of wave has to travel through a medium, or it has to travel through some kind of matter. That's why if you want to have a nice speaker system in your car, you need to make sure you design a box that will maximize the vibration, hence have a better sound. And this is exactly why there is no sound in space. So if you go up into space and you light a firecracker, you would not hear a thing. Electromagnetic energy, and that is produced by the vibrations of electrically charged particles, travels in waves, does not need matter to travel through. That's why you can see the stars in the sky. Does not need to travel through any kind of medium in order for us to see it. Electromagnetic energy, and basically that is light in the form of electromagnetic energy. Each color of light, Roy G. Biv, represents a different amount of electromagnetic energy, hence red, orange, yellow, green, blue, and indigo. No, it's not purple, it's indigo. Chemical energy. Chemical energy is stored in bonds between atoms. So those atoms are connected to one another, and whenever the energy is in those bonds are being used or broken, energy is released. Example, food. An apple has stored energy. Once we start to eat it, our body starts breaking those bonds and reforming new bonds in order to use the food so we can get the nutrition out of it, nutrients or nutrition out of it. Fuel, batteries, all those things are good examples of chemical energy, which is potential energy because it's stored for later use. Nuclear energy is stored in the nucleus of an atom. Now, the energy is released in two ways. Fusion, when you take two or more lighter atoms and you put them together to create a larger atom. For example, the sun, light and heat through fusion of hydrogen nuclei into helium. Hence, that's why the sun is such a powerful thing. And then we have fission, which is when you take those large atoms and you split them into two or more smaller ones. And then you have kaboom, atomic bomb. Now, all forms of energy can be converted into other forms. The sun's energy through solar cells can be converted directly into electricity. So, solar panels, alternative energy. Green plants such as trees, grass, and so forth convert the sun's energy, which is electromagnetic energy, into starches and sugars, chemical energy for the plants to use for later use. I think we call that photosynthesis. Yeah, that's what we call it. Now let's look at a few conversions and see if you can figure out what they are. What type of energy? Electromagnetic, and it's kinetic energy. What type of energy? Electrical, also kinetic. Heat from a toaster? Thermal energy. A ring from a cell phone? Kinetic energy, which is sound energy. So if you got your Snapchat alerts, your Kik alerts, your Facegram, Instagram, all those things are sound energy. A lump of coal. Now you have to think about, it's just a lump of coal. It's chemical energy, but it's potential because it has not started to be used yet. A moving bus. That is moving or mechanical energy. And it's kinetic because it's energy in motion. Now, examples of the law of conservation of energy. Now, remember I said earlier that energy cannot be created nor destroyed. It only transfers from one form to another. So let's look at some examples of everyday conservations of energy. A ball rolling down a hill moves from gravitational potential energy to kinetic energy. That was simple. A light bulb. You plug it in, that's electrical energy. You turn it on, convert it to light or electromagnetic energy. Electric oven. No brainer. Electrical energy converted to thermal energy. Battery powered flashlight goes from chemical energy because it's stored chemicals in the battery converted to electromagnetic energy. A tree. Electromagnetic energy, light from the sun. It goes to photosynthesis, chemical energy, starches and sugars that the plant uses to grow. An iPod, chemical energy, and that's stored in the battery, converted to sound energy. Solar panels, electromagnetic energy from the sun, converted to electrical energy. Nuclear power plants, nuclear energy. So we have fusion going on, a little bit of fission here or there, converted to electrical energy. Wind farms, if you live in California, you see a lot of these. Moving mechanical energy, that's the propellers moving, converted to electrical energy. A dam, or more properly known as hydroelectric plant, you have input from moving water, which is mechanical energy, and those water moving through the turbines at the power plant turns turbines, produces electrical energy. A TV, you have chemical energy, converted to sound energy, converted to electromagnetic energy. Fire, chemical energy, converted to thermal energy, and then converted to electromagnetic energy. The sun, we talked about fusion, nuclear energy, converted to thermal energy, we feel the heat, and we see the light, electromagnetic energy. A car, that's a nice looking Audi. Chemical energy, because it's stored in a battery and you have fuel, converted to electromagnetic energy, hence being able to use lights in the car. And sound energy, because you can hear the engine. And moving, or mechanical energy, hence the wheels will be able to turn when you push on the gas. Of course, it's got to be out of park. And that's the end of our lesson. So make sure you take a good notes. Make sure you review these notes and come up with some questions if you have any, and I'll see you in class. Have a good day.